The last lesson of this section is over rational functions. And just like the last section, we actually aren't going to go through the entire thing. Really, I just want you to understand some of the foundations of rational functions. So to begin with, a rational function is any function where you've got variables in the denominator. You may have one in the numerator, but the most important part of a rational function is that variables exist in the denominator. And the value of the denominator can never equal 0. That's going to become important when you start looking at the domain of the function. A reciprocal function is the simplest rational function where the variable in the denominator, it's essentially the reciprocal of y equals x. The domain of this function, meaning the values that you're allowed to put into x, is from -infinity to 0 and from 0 to infinity. The parentheses are here because -infinity isn't a number you can actually plot. Neither is positive infinity. There's a parenthesis here at 0 because it will go all the way up to 0 but not include 0. Here's the graph of the function. If you look at the range, that means all the y values. It starts at -infinity and it's going to increase towards 0, but it'll never actually touch 0. And then from almost 0, but not quite, all the way up to positive infinity. So that's your range. This function is constantly decreasing, as in these y values get smaller and smaller and smaller and smaller infinitely. Then they have to skip over 0 where they're way, way up here, and then again they continually decrease. Rational functions have what we call asymptotes. Asymptotes are lines that the function approaches. A vertical asymptote can never be crossed. A horizontal asymptote can be crossed, although we actually won't go through too much of that in this particular lesson. There are also what's called oblique asymptotes, and we will take a look at that as well. Alright, so for this next problem, we're going to graph y equals 4 divided by x. We could factor that so that it's y equals 4 times 1 divided by x. So just like when we were looking at quadratics, we are actually going to be stretching this function vertically by 4. To plot these points, or to graph this, I would actually plot a few points. We can't plot x is equal to 0, but we could plot a few points, like if x is 1, y is 4, and if x is 2, y is 2. If x is 4, y is 1. So I've got this one here, I've got this one here, I've got that one here. I'm going to do something like this. I should also plot some negative values, so if x is -1, y is -4. If x is -2, y is -2. If x is -4, y is -1. So those points would look like this. Here, here, here. The domain of this function, or the values that we are allowed to enter for x, are all real numbers, excluding 0. So we could say that x cannot equal 0. The range of this function goes from, that's the y values, starts at -infinity and goes to 0, although it'll never actually touch 0. So that would be -infinity to 0. The union of that with 0 to infinity. We can graph these on our calculators. Now, if you hit the button that says Mode, and you go to the one that says Connected, that's actually going to draw in your asymptote. Sometimes it's helpful to see, sometimes it's not helpful to see. So simply be aware of that when you're graphing on your calculator. We can graph these on our calculator. A lot of times it'll be really helpful to graph them on our calculator. Today I'm not going to because my calculator has died. But we will just do this by hand because it's pretty simple. Taking a look at the function, it says to give the domain and range. So again, I'm going to list some x and y values. So at -2, y is 1/5. At -1, it's 1/4. At 0, it's 1/3. Now you might be thinking, wait, I thought you couldn't put a 0 in. Well, 0 minus 3 is -3. I'm allowed to have that in a denominator. At 1, it's 1/2. At 2, it's 1. At 3, that's where we get that undefined. So this is where we're going to have our asymptote, is at x equals 3, although that's a terrible asymptote. Let me draw that again. At 4, we have -1. At 5, it's -1/2. At 6, it's -1/3, and so on. So if I plot this, maybe there's a 5th, and there's a 4th, and there's a 1/3, and there's a 1/2. And at 2, I've got 1. And I know I've got an asymptote there, so this graph is going to do something like this here. And then on the negative side, this one is going to sort of mirror that. So that's what this graph is going to look like. The domain, in this case, is that x cannot equal 3. The range goes from -infinity to 3, but it doesn't include 3. And then from 3, not including 3, to infinity. The next reciprocal function that we'll talk about is 1 over x squared. Again, it's another pretty basic function, but what you should notice in the graph is that it only exists above the x-axis if it's positive, and then envision if it's negative, it'll exist below. So this actually increases here, getting bigger, and then decreases over here. Our domain is the same, but in this case the range starts at 0 but doesn't include it and moves up. On this example, I actually want you to add to your equation that we're going to actually subtract 4 from it. And this time, rather than plotting points, we're going to be a little bit more logical about domain and range. Because we know that this graph starts normally at the x-axis and moves upwards, the first thing that I want us to do is take a look at this. Remember in trig, that number tacked onto the end, that constant, was a vertical shift? Well, it's going to do the same thing here. So this is going to be an asymptote. Now, I want us to take a look at this denominator. We know that we cannot have a denominator of 0. So what value of x would give us a denominator of 0? In this case, it's 2. So I'll have an asymptote here. Because I know the shape of this graph, I can now simply sketch it. The domain is all values of x except for 2. the range starts at -4, but doesn't include -4, and goes to infinity. Now, in your notes is a huge piece that's called determining asymptotes, and it tells you, depending on the type of asymptote, how you can find it. So the first thing that we're going to do is find all of our vertical asymptotes. Our vertical asymptotes are going to be related to the denominator. Write that down, vertical asymptote on the denominator. So we set our denominator equal to 0. Guess what that means? That means we have 2 vertical asymptotes for this particular function. The first one is at x is equal to -4, and the second one is at x is equal to +4. So when we write this as our answer, those are our vertical asymptotes. The next thing we do is look for either a horizontal or an oblique asymptote. An oblique asymptote actually is slanted. So here's what you need to look for. If your numerator has a lower degree than the denominator, then your horizontal asymptote is at y equals 0. So that's what we look for. Does my numerator have a lower degree than my denominator? Well, the denominator has a degree of 2 because it's x squared. This has a degree of 1. So I would say yes, it does have a lower degree than my denominator. So my horizontal asymptote is at x equals 0. Taking a look at the next one. Again, we start with the vertical asymptote, we start with the denominator. I'm going to set it equal to 0. So I have a vertical asymptote at x is equal to -1/2. When I'm looking for the other asymptotes, again, I'll start with my list. Does the numerator have a lower degree than the denominator? Well, in the denominator the degree is 1, in the numerator the degree is 1. So that rule doesn't apply. Do they have the same degree? Well, yeah, 1 and 1. Is the function such that we've got something times x to the same power as something times x to the same power? If that's the case, then we're going to have a horizontal asymptote, and the equation for that is going to simply be y is equal to 3/2. These x's have the same degree. Our equations are in the same format, so the horizontal asymptote is simply the leading coefficient divided by the leading coefficient. And for the final problem, first thing we do is look for the vertical asymptote. I set the denominator equal to 0, and my vertical asymptote is the line x equals 3. Now I look for the other asymptotes. Does my numerator have a lower degree than the denominator? Nope, it sure doesn't, because squared is bigger than to the first power. Do they have the same degree? Well, like I said, 2 is bigger than 1. The last one, if the numerator is of a degree exactly 1 more than the denominator. So the denominator has a degree of 1, the numerator has a degree of 2, so the numerator is exactly 1 degree bigger. Then we will have an oblique asymptote, meaning a slanted line. What we need to do is divide the numerator by the denominator. That's our first step. So remember how to do that? We pretty much just do synthetic division. So we have our 3, 2x squared, 0x plus 5, the next thing that we do, if we write this out, we have 2x plus 6 plus 23 over x minus 3. We disregard this remainder, and our oblique asymptote has the equation y is equal to 2x plus 6. I encourage you to graph this particular one on your calculator with connected mode set up so that you can see what an oblique asymptote looks like.